Okay, now let's talk about the p-type semiconductor. So a p-type semiconductor is where the dopant atoms are of trivalent nature, or they are trivalent atoms, which means that they have 3 valence electrons in the outermost shell. So I have taken this crystal structure lattice of germanium, where one of the germanium atom is replaced by indium atom. Now the 3 valence electrons of the indium atom will be making 3 covalent bonds with the 3 neighboring germanium atoms, while the 4th covalent bond is not formed because of a deficit of electron. So in order to fulfill this deficit, one of the electrons from the neighboring germanium covalent bond will break away and then go and fill up this deficit and form the indium germanium bond. So when this indium takes up this electron, then what happens is this indium will become negatively ionized, negatively charged. It becomes ionized with a negative charge. Okay, while the electron which has broken from the germanium bond will leave a hole behind, which is a positive seat. So as a result, again on a whole, the atom is electrically neutral. So it doesn't mean that the p-type semiconductor will have an excess of positive charge. So atom has a positive charge. No, the atom still remains electrically neutral here. Now since each of these trivalent atoms are producing one hole, okay, so if you have, let's say have 4 trivalent atoms in this crystal structure, you will have 4 holes produced by them. So these atoms, like these indium atoms, therefore, since they are taking up electrons from the neighboring germanium covalent bond and breaking and getting ionized and resulting into a hole, therefore they are known as acceptor atoms. Like in the case of n-type semiconductor, the pentavalent atoms were known as donor atoms because they were giving that 5th electron for conduction. Again here, as your temperature increases, the other covalent bonds between the germanium will break up, resulting into an electron and a hole. So the total number of holes on a hole is always greater than the total number of electrons. So we can say the holes therefore are becoming the majority charge carriers here, and the electrons are becoming the minority carriers. The number of electrons being lesser, so they are minority, and since the number of holes are much larger, so they are majority. They are in majority. And again here also you will have the total current as the sum total of this electronic current and the hole current. The electrons are present in the conduction band. The ones which are obtained by the breaking of a germanium bond, the electron which is released is available in the conduction band and can conduct electricity, resulting into an electronic current, and the holes are in the valence band, resulting into a hole current. Okay, now again these holes which are obtained from this indium atom, in the energy band diagram, they again create a discrete energy level. Okay, so I should draw this with a dotted line actually. So it creates a discrete energy level. So a discrete energy level is created in this energy band diagram, which is known as the donor